Starting soon, guys. Just gotta find all my stuff. That's right, it's not until 5 past, everybody. You can just cool your jets. We're back. Ready for COMP2300, week 5. Someone asked on the chat whether I composed the intro music. No, I did not. The intro music is by a musician called Dano Song, I think. I guess he's called Dano, and he has some royalty-free music available. And this is a song called Feeling of Sunlight, so if you want to get into it, you can go there. Dano offers a license for his tunes, so I paid him for a license so that I could use it in all of our lectures, because I thought it would be fun to have a catchy theme tune just to get everyone into a COMP2300 mood before our lectures each week. So just going to be a few more minutes before we start, or a few seconds really. Just want to make sure everything is working out. We're live in Restream. Video. I hope it's working in Microsoft Streams. It's always a bit confusing whether things are working in Microsoft Streams or not. Just check that there. Oh, it's working. Cool. I'll turn off the audience view. I don't want to waste bandwidth. I was much less worried about the... oh, there's Emacs in here somewhere, I think, but maybe not on my screen right now. I do tend to use Emacs for a lot of editing, although for COMP2300 we all use VS Codium, which is great. I think it would be a little bit much to impose on Brent to remake the whole COMP2300 extension in Emacs. That would just be a bridge too far, perhaps. I'm just going to check to see that everything looks good here. That's VS Codium. Here I am. I just have to make sure that I'm actually in the shot and not randomly out of it. I might put myself to the small version on the right-hand side, even though I like being the focus of attention. Some of you guys like to actually read the slides, so that's a comment I've gotten, is that you like reading the slides. I'm just going to adjust my browser here. When I look down here, I'm looking at my laptop where I've got the chat open, so I can keep in touch with you guys. Okay. No, I need 2 windows at the same time. Come on. Close that. Yeah, so now I think we had a bit of a talk about chat last time, so I think the protocol is this. I don't mind where you chat. I've got the chat from YouTube and Twitch combined on my second screen here. And then we've also got the chat in Teams. But you guys can say whatever you want in Twitch and YouTube chat. That's sort of back channel. That's fine. I'm not exactly going to track what's going on in there. But we've got tutors looking at the chat in Teams. Mitchell is going to be there. So if you have a question, put it over into Microsoft Teams, and then that makes it a little bit easier so that everyone can keep up with the questions. We can make sure to address anything that's a bit more tricky later. Okay, well, if everything is rolling and happy, then we might get started. I can see that we've got about 30 people watching this afternoon. Thank you so much to all of you for connecting. Today's topic is the stack, although we sort of hinted at this last lecture. In this week, we're focused on how you get stuff done in your on your disco board in assembly, how you're getting stuff done through functions and how you're actually going to do like everyday addressing in memory that will really help you to get interesting stuff done in the assignments once they start to get a little bit more complicated. Some of you might be starting to explore this stuff for your assignment ones, but certainly everyone will have to start getting into this stuff in the other assignments for this course. So just to recap where we were, oh, I've skipped a little bit. We previously talked about a calling convention for functions. So this was going to be a set of conventions that we as programmers all agree to help us write functions that play nice with each other. Oh, I should actually start my recording. That's the one thing I always forget. Oops, start recording. That's why I turn to the screen, not just to look at myself. Now it is recording, good. Oops. Yeah, so previously we were talking about calling conventions, what you have to do in a function to make sure that you're not going to mess up other code in your program, and how you can, what you might have to expect if you call someone else's function. So not everything is going to be sort of left the way it is if you call someone else's function, and you will have started to find out how that can mess you up in assignment 1. If you call a function with some data in R0, you might find that when that function returns, R0 has been changed and your data is gone. So how do you know which things you're allowed to store data in and which things you're not? Well, that's what the calling convention does. So the calling convention gives us a document which sets out everything that a procedure or a procedure is supposed to do, data that it must leave in the same place, leave the way that it found it, and data that it's allowed to change up and mess around with during the function, and it doesn't have to clean up after itself. So just in short, we spoke a lot about how data would go into functions and come out of it, and so far we've only been talking about that with respect to registers. So our registers were going to give us a way to put information into our functions and a way to get information back. So far our calling convention is completely about the registers. Uh-oh, slides may be zoomed in. Thank you, people, for reminding me that OBS is not looking good. I must have changed my screen resolution. Oh no, yeah, there we go. Come on, Charles, get it right. You know I'm a real streamer when my stream system has to be adjusted in the middle of the show. That's how you know I'm doing the right thing. Oops. This is lucky that I have Mitchell in the chat. If someone really wants to get my attention, you can @ me in the chat and my computer makes a little noise. So that's a good way to warn me that everything is going off the rails. It looks good, that looks good, that looks good, that looks good, that looks good. Okay, back to right-hand side. Does that work now? I think so. Right-hand side small. Back to my functions. This is recap, so it doesn't have to be right. So the calling convention has a lot of detail in it. It's a document which you can look at on the resources part of the website, but it does set out where your function would expect to find parameter values, the inputs, and where it should leave outputs. And it also gives you some rules about which registers a function is allowed to mess around with without any concerns about what the consequences might be, and which registers have to either be left alone, or if you're going to use them, you need to save them somewhere else and get them back. And we're going to work out today how we use the stack to actually do that operation of putting things back the way they were. So here's the details which are going to be important so far. Out of your 16 registers, R0 through R15, when a function is called, you're allowed to use R0 and R3 as registers for parameters. So you can send it 4 32-bit pieces of information through those registers. Or if you wanted to, you could combine them into 2 64-bit bits of information or one 128-bit bit of information. That's fine. Those registers, the first two are the result registers. So if your result is going to be less than 64 bits, or some kind of bit of data which is less than that, you can put it in R0 and R1 and return it to whoever is called the function. In between the function starting and the function ending, the function can do whatever it likes in R0 and R3, and it doesn't have to clean up after itself. So if you leave some function in R0, or some number in R0, you call the function returns, R0 might get changed, even if the function is not supposed to return a value. On the other hand, R4 until R11 are so-called callee save registers. So these are ones that a function is allowed to use, but if they use them, they have to put them back the way they were before the function returns. So they're the callee save registers. We've got some other registers, R12 to R15, which are special. So the interprocess pointer, the stack pointer, the link register, and the program counter. 12, 13, 14, 15, that's 4, yes. These registers have a different purpose. Obviously, PC is where your program is up to executing code. The link register is something that you'll definitely have to save and restore if you're calling any functions within your function. We learned that last week when we were talking about nested functions. The stack pointer is something which you are changing. We'll learn how to do that today. The IP register we don't use in this course. It's something which is more interesting to compiler designers than for us. But these are called special registers by the procedure call standard. So they're something which have their own rules. Someone's just asked in the chat, Ryan has said, why aren't you supposed to use R2 and R3 as result registers? Well, it's not that you're not supposed to, it's just that the default in the standard is that the result registers are R0 and R1. There are some times when functions have a result which can be returned in a register, and sometimes the result might be something like a string where we don't know how long it's going to be, and it might be much longer than 64 bits. And in that case, we're going to have to return it somewhere else. A good place to return it would be in memory, right? Not registers. So we'll discuss that a bit in this lecture. So R0 and R3 are the registers called scratch registers. So these are the ones your function is allowed to freely use. And in many cases, those 4 lower registers are the ones that are used most often. You're using them all the time just to get a little bit of work done. That's why we call them scratch registers, because you're just writing over them all the time, always doing little bits of work with them. Okay, now we get to the new content for this lecture, parameters and return values. So I've talked about how we can use registers as parameters, registers to store our parameters and bring them into a function, and how we can use registers to return a value. But there's other options as well, other options. Here's 2 examples. We've got a function called +1. And this is doing a very simple task. It's taking a value in, adding 1 to it, and returning it. This doesn't require very much code, but both of these functions are actually doing the same thing, but they're doing it using a different style for taking a value and returning it. Now, in the first instance, we're assuming that x, the number that we want to add 1 to, is going to be in R0. And then when we return, we leave our return value in R0 as well. So that's used sort of the register style input and output for a function. Now, often when we're in higher level programming languages, we would call something like this pass by value, because you actually have to, if you're using your x somewhere else, you'd actually have to copy it into R0. You've now got a copy of x. Your function then goes and operates on that copy of this, this value, and it changes it in R0. And then it says, okay, well, here's the value back. It gives you back your actual value, which has been updated. In the second version, we're going to assume that our R3 is actually on the stack. So the stack is going to be a section of memory. We've got more diagrams in a bit. Memory going down, and it's got a bunch of chunks in it. Each chunk is 1 byte. We know we've got byte addressing for memory, and might be these four are designated to hold R3. So our stack pointer is going to point to that one. Finally got my Wacom tablet to work this week, so it's a little bit easier to write here. So this is going to contain our number that we want to operate on. And here we're going to load into R3 whatever we had been storing in SP. Then we're going to add 1 to it, add R3 plus 1, and we're going to put it back in memory, put it right back where we found it. So in this case, rather than passing the value directly to the function through a register, we're just suggesting that the function knows that it has to operate on a value in memory, and it knows its location. We might have some way of sending the location to the function as a value, but in this case, the function just assumes that it's the latest thing on the stack, and it can then operate on that directly. So this is pass by reference. Two fundamental ways of getting data into and out of a function. And you'll notice that in this second option, we're not using R0 and R1 at all. So we're not leaving anything in R0 and R1 for our caller to see. If we'd been passing something back to the caller, then we would have to put it in R0 or R1. Okay, so the two different approaches to passing parameters and return values in and out of functions. The difference here is that the pass by value has to make a copy of it. So your caller would have to put its value of interest into R0 and then get it back afterwards out of R0 and put it where it needs to use it. Whereas the pass by reference is just giving the callee access to the same bits as the caller. So in this case, the caller could have been using that value on the stack already, and it just gives the callee, says, okay, it's going to be an SP or wherever the stack pointer is pointing to, and you just need to go and do the work on that, and I'll look at it later and find it. So the caller doesn't have this responsibility of moving values in and out of memory, for instance. So that's pass by value versus pass by reference. There are pros and cons to both. It really depends on what kind of a task you're trying to do. Now this is a critical point at this part of the course. I think I've mentioned this before when we were just introducing memory operations. In general, data needs to live in memory to write significant computing programs in assembly. You can't just use your registers for everything. And if you're trying to use registers for everything, eventually, and within this course, you'll come up against problems that you can't solve. So you need to have a more permanent place where you can store your data, where you're in control of data structures and you understand where things are. You need to be using memory operations for it. So registers are not for long-term storage. There are functions which are going to wipe out the values of R0 to R3. You already know that now. And in latter parts of the course, you'll be dealing with so much data to do operations that if you aren't using memory to store it, then you'll run out of registers. Or at least it'll be very difficult to get through those situations. And your code will be a mess as well. So really you need to make sure that memory is the place where your data is living most of the time. Big picture here, we've been talking about simple functions that fit on slides. You need to be doing a lot of practicing to make sure that you can work out these details, and particularly with the memory stuff that I'm going to talk about today. It's something which needs a lot of practice to get the handle of. So we can do a lot more examples today and get through some of these trickier topics. Now we get to the function of interest. The topic of interest is the stack in this lecture. There's been interest in the chat already about the stack. It's coming to get you. It's here. It's going to solve all our problems. I think I'm going to assume that everyone knows what a stack is. I think that it's something that you would be taught in your first year programming courses, but just as a little bit of a refresher, if you've forgotten, a stack is a data structure, and the idea is that you're putting data in kind of a pile. Okay, so if you're making a pile of data, imagine that you're stacking up plates, for instance. You're going to put one plate on the bottom, that's going to live here, and then you're going to put another plate on top of that, you're storing a bit more data, and you put another plate on that, putting a bit more data in there, and stacking them up. And then now you've got your data in a stack, and the easiest bit of data to actually access is this one right on top. So the stack as a data structure is called like first in, last out, right? So as you're adding data, the first one that you added here, 1, 2, 3, 4, the first bit of data that you added is going to be on the bottom. And as you're deleting things, removing them from the stack, you can only delete them from the top. So this one's going to get deleted first, 4, this one will get deleted second, that one deleted third, and that one deleted fourth. And then you can start stacking up again with new numbers. You might have used up 1, 2, 3, 4, you don't need them anymore, now you want to store 5, 6, 7, 8. So it's a kind of a very simple data structure with what we call like one pointer that identifies where you are up to in the stack. So if these bits of data were going into memory cells, then our stack pointer, this might be free memory up here and we've got used memory. In our case, the stack pointer is going to be up to here. This indicates where we're at in the stack. Yeah, very simple data structure. If you need to know more about the stacks in general, that's a little bit of revision that you should be doing. But for the rest of this lecture, we're going to talk about stacks in the specific, one kind of stack, which is implemented in ARM v7 as part of how your disco board works. You can implement other ones if you want to, but we're going to talk about kind of the default implementation. So last time we were talking about some open questions, and we're up to, we've now addressed this one. How does the program know where to come back to? The link register. How we get information in. Oops, we can use registers or we can use memory. How we get information out using registers or memory. And now how can we have some scribble paper? So the answer is going to be the stack. Where do we put data when we're just using it within our functions? How do we implement local variables? What if we have to store something complicated? Our default storage place for everything is going to be the stack because it gives us such an easy way to construct data in and then remove data and get back to where we were. So this is the question of what we do in this situation. If we had a function like this in a higher level programming language, we had these three local variables that perhaps we wanted to do something with. These might come in R0 and R1, and then we do some calculations with them and store them locally, and then we might do some other stuff that requires C, D, and E. This is not too hard. If we had a function like this where we only had these three local variables, then we can just put C, D, and E in some registers, right? We've got 16 registers minus the 4 that have special uses. So we've got 12 places to store a 32-bit number. That should be fine. Even if C, D, and E happen to be 64-bit numbers, we'd probably be okay with registers until we started to do operations with them. But let's have a look at a different kind of function. Again, a high-level programming language. This function is going to have two local registers that are have much more complicated data. This first one has a kind of struct here, a kind of little dictionary with some keys and values. And one of the values is going to be an array. And then we've got some big array which we want, and we want to just have 1,000 items in it, right? So we don't have 1,000 registers, we've only got 12 free registers. And if we're don't want to use our scratch registers, then we've only got 8 free registers. So we really can't use the registers to store all this data. We have to put it somewhere else. So this time there aren't enough registers. And that's where the stack comes in. It gives us a default place where we can start to store local variables. So just revisiting the stack pointer from last lecture. The stack pointer SP is a regular register. It contains a memory address, and this memory address is going to be used as the point where you're up to in the stack, where you can add data after that, and where you have to start removing data if you wanted to delete stuff from the stack. So you can use the stack through its stack pointer to save values in registers that you don't want to be overwritten. So for instance, LR, that was the one we were really worried about last time. You can use the stack to pass parameters in and return values, just as we did on the previous slide. And then you can also use it for temporary variables, just like a kind of scribble paper. So it's useful for that as well. The stack, as I said, it's in general used as a first in, last out data structure. You've got 2 main operations for a stack. One operation is push, where you take some value and you put it on the stack, just like adding a plate on top. And then the other value is pop, where you're flicking that plate away, you don't need it anymore, and your stack pointer goes down to the previous value. So that's SP and the stack pointer. Now, the caveat with all of this is that you're an assembly programmer now. That means that if you want to, you can completely mess this up. The compiler is not, there is no compiler, and the assembler is not going to complain if you do it completely wrong. So you need to make sure that you're doing operations with the stack correctly. And if you get into trouble, it can be a little bit difficult to debug, to work out where you've gone wrong. So you have to be careful, document as you go, follow the rules, and tread carefully when you're using these operations. They shouldn't be scary though, right? You're an assembly programmer. You've got the power to mess things up completely, but you've also got the power to fix them. So I believe in you guys. So the stack doesn't come for free. You actually have to set it up. The trick here is that we already set the stack up for you in all of the startup code that you get for your COMP2300 work. So if you have a look in the startup file, oops, too far. Just build this so I get the startup file visible. Okay, here's my startup file. This is the first actually executed operation is putting this number, E stack, the start of the stack, into SP. So this is giving us our, this operation is setting up the stack for our use for the rest of our program. Now this value E stack is defined elsewhere, but here's what it is, OX2001800. And it's actually set at the end of RAM, which is a bit weird because I was just saying you were going to add stuff to the stack. And if you keep adding, of course, you'll go off the end of RAM. But the stack doesn't work that way in ARMv7. By default, we actually use a negative stack. So we're sort of adding minus numbers every time. It's an upside down stack. A little bit difficult to conceptualize, but I guess this means that in our SRAM, our low numbered memory is kind of free for our use. If we want to just put something in OX2 followed by 7 zeros, no problem, and the stack lives at the top. By the way, if we have 18000 bytes of memory, how much memory do we have on our disco boards? How much SRAM is there? I'll let you guys figure that out. So here's the stack pointer in memory. This is where it starts at the start of your program. You've got, this is the starting position. OX2001800. Now this one is grayed out because this doesn't exist, right? This is not accessible SRAM. And if you try to load from that or write to that, it won't work, as I found out last week or last time when I was trying to use it in an example. This is where we get to some of the tricks of how to, or the rules of how to operate the stack in our disco boards. And the first rule is that the stack pointer is always pointing to the start of the previously written piece of information. So when you haven't written anything to the stack pointer is pointing off the edge. And the first thing you do before you get to write anything to the stack is to move that stack pointer down a notch to here. It always gets moved down, or you should always move it down 4 bytes so that you can store a register value at least. You can move it down as many bytes as you want, but that's the first rule, is you have to move it first, then store your data. So this value, remembering SP as a memory address, is always changing as your program runs. It's never staying the same. As you run functions, the SP changes all the time. There's there's maybe 2 dimensions of configuration for stacks in general. One option is full stack, the other option is empty stack. In full stack, the SP points to the last occupied address, and that's the configuration we use on the disco boards. In the empty stack configuration, SP points to the first unused entry. That's not what we do. In general, you don't have to worry about your absolute SP address because you're using it mainly for offset and relative addressing. You don't need to be too concerned about exactly what it is. Here's the other dimension of configuration for stacks. You can either have growing stacks that ascending stacks through memory, or descending stacks that go down. So on the disco board in ARM Cortex-M, the convention is to use full descending stacks, starting at the highest address in the address space. Yep, so we're going to do a lot more examples. This will become a little bit more clear over today's lecture, I hope. Okay, stack instructions. Now we're finally where we want to be. You know what the stack is, you know what SP is, it's pointing to it, but how do we actually do stuff with the stack? Here's an example of a program that's doing something with the stack. We're just going to use SP just like any other register containing a memory address. We don't have to worry exactly what it is. So the goal of this bit of code is to store a value. That value is this one, OXFE. And we want to put that on the stack, and then we want to get it back again. So we're going to push it to the stack and then pop it off the top of the stack into a different register. So the first thing I'm going to do is, here I'm doing an offset store onto the stack. Now you remember that our memory addresses are bytes, right? So our stack is going to point here, somewhere else, occupied memory or off the edge, we don't know, we don't care. We just want to make sure that we write our value to the next 4 bytes of available memory, which is the 4 bytes below. So SP is currently there, and we're going to write it to this SP minus 4. SP minus 1, minus 2, minus 3, minus 4, yep. So this is going to now contain that value in R2. And then we're going to update our stack pointer to the decremented value. So I did say you had to decrement the stack pointer first. We're just doing it in a slightly different order here. Okay, then we've got our opportunity to do some stuff. We've saved our value in R2. We can do whatever else we want to do. And then finally, we want to get it back. Suppose I want to get back into R3. Well, I have to load it. SP is still pointing to this location. It's pointing to this new location after I'd decremented it. We can load that back into R3, and then we're going to add 4 to SP to put it back where we started. Okay? I'm going to show you again with diagrams so that it makes a lot of sense. It's good to see things a couple of times when they're new. So here's the push bit, just the push part of our operation. Whoops. We're going to start with our stack pointer somewhere. And we know that all of this memory is already occupied. We don't care what's there. And we've got OXFE in R2. Now we're going to put the write OXFE into memory. We're going to write it into this location, OXFE. Very poor writing, but it's a bit difficult with a stylus. Then we're going to move the stack pointer down. So at the end of the push operation, OXFE has been written into this unused memory, and the stack pointer has been moved down. So OXFE is still in R2. It hasn't gone anywhere out of R2 unless we decide to write over it. And we know our stack pointer is now where it started, -4. When we do a pop, our stack pointer is pointing to memory, so the memory we were interested in, so we can just load it. That puts OXFE back into R3, and then we increment our stack pointer and push it up back that way. So then our stack pointer is back where we'd left it, in the first place. Yep. Someone in the chat's just asked, why does the stack pointer start from a memory which is already occupied? That's just the way we're configured. This is the full stack configuration. The other option is empty stack, where the stack pointer is the first bit of unoccupied memory. It's probably one of these things which is just chosen over time and becomes a standard. But I can think of one reason why it might be useful to do it this way. If your stack pointer is always down a set amount of memory, but you want to push something which is more than 32 bits into your memory, you'd have to then move the stack pointer anyway. So if often you're not sure how much you want to move the stack pointer, in this case, you always have to move it regardless. So it may as well just sit there at the last occupied bit of memory. Then it's always convenient to load. It's a little bit more effort to store, but maybe you're going to put that effort anyway because you're not sure how much you want to store until you start running your program. So that's just one reason why we might choose this configuration. So the missing values in this diagram, more specifically the SP values, which we don't know what they are, we don't know what memory addresses these are. These values aren't empty, they're just unknown. And in fact, when you're operating with the stack, it's quite freeing because you don't have to know so much about what address you're at in memory. You just know that the stack has been set up for you. When your function runs, it can start doing stack operations. It can clean up after itself, put things on the stack with push, clean up after itself by popping, and then everyone is happy. So it's quite freeing, but you don't get to worry about the details as much. And if you're really concerned about what memory address you're using at any particular time, maybe it's a little bit unsatisfying. Yep, you're very welcome, commenter. So I've shown you how to do stack operations with 2 lines of code, but maybe this is going to blow your mind. You can just do it with 1 line of code. In fact, if you look on your cheat sheets, there's quite a bunch of load and store operations down here, which are more or less completely dedicated to doing stack operations. So we're going to go through them in this lecture. But this one's called offset load and store with write back. So the idea is that you're going to do a load or a store with offset, just like we were already doing, but then at the same time, you're actually going to write the offset value back into the base register. So we can do this with any register. We don't have to use SP. This is the pre-offset version of this operation. So if we wanted to store R0 in a value in memory that was +4 from R1, so this is going upwards in memory. If our memory was, I need to have a little pop-in thing that brings in a memory diagram. R1 might be pointing here to that bit of memory, 1, 2, 3, 4. And we'll move it up to there. +1, +2, +3, +4, yeah. So we want to move R1 to there. and then write some data to it. We're going to store whatever is in R0 in that. Now note we've got this exclamation point here, and that's what turns this from a regular old store offset operation into a write back operation. It's going to first increment R1 by 4, write that value into R1, and then do the store. The post offset version is going to update the index register after doing the load. Okay? This one was before and this one was after the load or store. In this case, this is handy for this situation. We've just, supposing we had a positive stack, which we were setting up here with R1 as our pointer to it. This first one is going to push something on the stack, and then this one's going to pop it off. So this operation is going to load from R1. It's pointing to here, so it's going to load R0 back into R0, whatever that value was, will go back into R0. And then we're going to move R1, not 4 bytes down, but actually 8 addresses down to somewhere down here. So this is going to be the new R1 after we've done the load. So pre-offset, that means you're changing the index register before the load, post-offset after the load. And just be careful about how this syntax works. The exclamation point here is for pre-offset, and then post-offset is a comma after your command, and then your number for your offset, and there's no exclamation mark needed for post-offset. Okay, it's a little bit tricky to work out, so I encourage you to do a little bit of exploration with the cheat sheet on your own, and we'll do an example in a minute. So here is a diagram just to illustrate this idea of pre-offset addressing. We're going to start with a base address and our base memory cell, and we've got some address space. And the first thing we do is take some offset address and change our register value for there to that one, which is where we want to do our operation. And then this is our destination memory cell, whether we're reading from it in this case or writing to it, which would have the arrow this way. Both ways work, pre-offset addressing. And the write back means that that new address gets put into the first register. Post-offset addressing, this means that we use the first address as our destination address, whether we're loading in this case or storing. Then we do the offset, and then we do the write back. So RB now points to this new one. Pre-offset, post-offset. So this is great. This means that we can now do operations with our stack pointer with fewer addresses. And this is a classic little pattern. We want to put OXBC again into the stack. We can first push it using store, but we're going to do pre-offset storing. So first we're going to move SP down 4 memory cells, 4 bytes, and then store R2 in it. And then when we pop, we want to load it back, but we want to do the offset afterwards, because when we pop something off the stack, we take that value that we've loaded there away, and then we move SP back. It actually, by the way, it doesn't overwrite this RAM. The RAM still has your data in it, but it's just going to get overwritten the next time someone else pushes to the stack. So we tend not to overwrite RAM, we just leave it how it is and wait for someone else to overwrite it when they need it. Yeah, I might do a demo of this. I just want to see what's coming up. Oh yeah, we're going to get through a few more instructions before we get to a demo. So in fact, when you're doing this operation, these two stack push and stack pop, these are such common operations that there's a specific push and pop instruction in the ISA built into your disco boards, which will do this for you in one command. So you don't have to remember the SP or this kind of complex syntax much of the time if you're just doing this with the regular stack pointer. So push R2 is going to give the same result as store R2 post offset, pre-offset -4, and pop R3 is going to do exactly the same thing. So that makes things a lot easier actually. You have to just remember here that the SP base address is implicit in these operations. In fact, this gets even more easy sometimes because you can use push and pop with a list of registers, not just one register. You can get a bunch of registers together which you'd like to push onto the stack and just do something like this, push R0-R2, it's going to push R0, R1, R2, and then R9 onto the stack, and that will do all the decrements that you need for you. And similarly, you can pop them back. As long as you have them in the same order in your commands, the right piece of information is going to go into the right register. Register lists, so that's really, really handy. I think the next, I'm forgetting where I'm up to now, but just to give you some context here, the push instruction encodes a list of registers into a number of bits within the instruction. This is the 16-bit version of the push instruction, which supports a register list. I think you're only allowed to do 8 registers, the lower 8 registers with the push encoding. We were having a bit of discussion about this with the tutors earlier. So if you want to push R0 and R1, then you'll have a 1 in R0 in this place and a 1 in this place and 0s in the other place. And that's how you represent within this instruction which registers should get pushed and which should get popped. We've also got other storing and loading commands which allow us to store multiple things at the same time. There's kind of 4 matching ones, or 2 pairs of them. And they've got 5-letter names, which are a little bit tricky to remember the first time. But the first 2 letters show you whether it's a load and store. And the M here means multiple, so it's load multiple, store multiple, store multiple. And now this one is going to do load multiple, decrement before. So it's going to figure out the right amount of memory to decrement to store multiple registers. This one means increment after, so it's going to be in a positive situation where you are moving back up a data structure towards higher memory addresses, and you want to increment your base register at the top. Whoop. Yeah, Adam says, is it possible to push LR and pop LR? Totally is. So I'm not sure how that works in the encoding. Adam, maybe you can do a bit of an experiment in real time on your computer and figure it out for me. But we might give it a try in a second. Someone's just asked if I could explain post offset again. Post offset means that your base register is going to be changed after the operation has been done. So your if you're doing post offset, then this might be whoops. I get into trouble where I can't use my chalk anymore. This one might be pointed to by R10. And if you did load with post offset, letter R3, comma, R10 plus 4, that's going to first load this value into R3. So now R3 is defined to be equal to OXFE. And then R10 is the address, which is now going to get moved up by 4 cells. Now R10 defined to be equal to R10 plus 4. So it's just about the order of these operations. And it's certainly spelled out on the cheat sheet, but sometimes the cheat sheet's a little bit tricky to parse. you better give it a go yourself. Maybe I didn't finish my explanation about the load, multiple, store, decrement before. This is the same idea. You're going to be pre-offsetting by decrementing down a stack, and this one is going to post-offset and it's going to be incrementing. So you don't get to choose the direction in this case. This one is going to store multiple, and do the decrement before, and this one's going to store multiple and do an increment after. So in these commands, you don't get to say what the offset is because it will work out the amount you need to offset in order to store the number of registers you want to store. Yeah, so I'll do a little demo, but before I do, I just mentioned that this is a tricky topic. I encourage you to do some reading. Now that we're up to this point in the course, you can be looking more deeply at this online textbook by Plants, which refers mainly to Raspberry Pi assembly, which is a little bit different. It's version 8, but you also have many similarities with that. So you can find out most of what you need to know, or find multiple different kinds of examples, different ones than I do in the lectures in that book, if you're having difficulty understanding this topic. So I'm just going to chill out for a minute before we finish up with our final slides, but I'd like to, maybe try an example. So I think we were talking about whether you can, how you might use these ones with a function. Suppose I wanted to have a +1 function. BXLR. So I've got my function ready, and maybe I just want to have my data passed by value using R0, no big deal. Now this works fine, but if I wanted to have a nested function, for instance, maybe mult2 R, well, I think, maybe I'll just add 2 instead. Add 2, add R0, 2, and I wanted to go to this one from within my +1 function. As we found out last week, I'm going to need somewhere to store LR before I do that. So actually I can just use push to store that and pop to get it back. So this will be fine. Let's just see that it works. Oh, I probably should have something in R0 to start with. Oh, come on. Okay, you're going to put R0, put 1 into R0, and now I go into my +1 function. First thing I do is to push LR onto the stack. Then I'm going to add 1, so R0 is now 2. Now I'm going to my other function, which is going to add 2 to it. R0 is now 4. This brings me back here, pop LR back, and now I can get back to my, whoops, no, it didn't work. Uh-oh. What have I done wrong? Maybe I jumped over the edge of there. If I had an ops here, it would have worked. I went from this position, which is actually going to be right in that function being called again. It was a bit of a mistake. Just show you how it works properly. I edited down last week's video by cutting out a lot of this, a lot of my mistakes in the live coding. When I'm live coding in a lecture, it does tend to have a few more mistakes. Pop, BXLR, and now I'm in the NOPS. So I'm in the NOPS, it's worked. Phew. Yeah, there's a bit of discussion going on in the chat right now about which order things get put onto the stack. I'm not sure. You can find out if you want to by setting some known values into your registers, doing a little experiment. but we can kind of end the argument by saying that push and pop are designed so that your order of registers in push and a matching pop should be in exactly the same within those curly brackets of registers if you want to put things back exactly as they were. So if you had LR, we can just push LR, pop LR. If it was LR, R0, R1, R2, we'd do that. R2. And that works, well, it should compile anyway. This one's going to overwrite our return value, which is probably not a very good idea, but it will work. Okay, so we've got push and pop. Yeah, I'm just going to take a little break and read the chat to make sure I've got everything here. I'm really impressed with the questions you folks are answering. That's really nice. See you guys trying hard. Yep, Benjamin Gray, as we'd expect, has the right of it. There's 96 kilobytes of memory accessible in SRAM on your Disco boards. So not that much, but we tend not to use it all in this course. It's a lot of memory if you're just adding in values by hand in assembly. Okay. I need to have a little interlude music so I can take a break and have a sip of water. I hope the sound is better this week, today. I was listening to the recording last time on headphones, and I found this really annoying high-pitched ring, which I think I can still hear. I've put a bunch of these things around to try to cut down reflections, at least on my desk and side to side of the walls. But it's a little bit tricky to cut down audio reflections in a small room. And unfortunately, I'd like to cover all the walls with like thick black fabric, but I've also got lights set up to reflect some light on my face so you can actually see me. And that would not reflect off like big black blankets. So we'll have to keep trying and see how we go. Okay, functions and stack frames. Now we're getting to more of what you would do if you were writing a more significant function, or the rules that you should take into account in general when you're writing functions so that you don't stomp on other people's data. So I'm going to talk about something called a function prologue and a function epilogue. So your prologue would be some code that runs at the start of your function to kind of get things ready before you actually do the work. And the epilogue is going to be where you tidy everything up after your function to make sure that you're not messing things up from other people. A few tasks which you'll have to do in your prologue. You'll have to probably store to the stack your LR, because you might be calling other functions inside your function. And you might store to the stack any other values, e.g. parameters, that could be in registers, which you could accidentally clobber during the execution of your function. So remember, the AAPCS gives you this guide to which registers you're not allowed to clobber. That's R4 through R9, I think. And then you might also decrease the stack pointer to make some room for your temporary variables. So if you were starting out a function and you know in your function that you're going to be doing some work with like a couple of integers or something, right? If you're writing in C, you might sort of put them as local variables at the top of your function. Int A, int B, and C. If you're doing this in assembly, you're probably just going to do something like move the stack pointer down. So if I had three ints, suppose I wanted them to be 32-bit ints, 32-bit int, 32-bit int, and I wanted to make space on the stack, I'm going to have to do something like just subtract from the stack. I don't really need to write to it. I could just say sub sp SP. What's this going to be? 32 bits, that's 4, 8, 12. So now I've saved some space in my stack pointer for these, saved some space on the stack for these integers that I might be accessing later. And then when I actually get back to them, I might access them using offset addressing. So if I wanted to get in my stack, maybe my stack pointer is now pointing here at int c. If I want to get that one back, I can just letter 0 sp. And if I wanted to get int a, I'd have to go +4 +8 to get there. -8. Oops, forgot the brackets. So this is just going to do some offset loading. But it's not going to change the stack pointer. I'm just remembering what that value was or storing to it. I presume this is completely clear because I haven't seen any discussion in the chat. Engineering 2219's representative in the Twitch has suggested I get some big white blankets. Well, that's a very good idea. I don't have too many big white blankets. I thought about putting up a bunch of foam and then putting white fabric over it, but we'll discuss that another time. So at the end of your function, you'll want to re-increment your stack pointer to free up this room that you were previously using for your temporary variables. So I had my A, B, and C, but now I don't need them anymore. So I can move the stack pointer back up, C, B, A, back to pointing to where it was before. Then I will have to restore all my stored values back to registers. The link register is probably the most important one. Make sure that the return value is left in the correct place. If it's in memory, make sure it's in memory. If it's in a register, put it there. And then restoring the stack state, basically putting SP back to where it was before my function started, so that from the perspective of the caller or the code which has called my function, nothing has changed except for maybe values in R0 to R4. So you're basically tidying up after yourself. So you should think of this kind of stuff as a share house kitchen, right? Many of you would be living in a share house or have some experience with a share house, and the biggest source of friction in a share house is usually how people leave the kitchen after they do their cooking or make their breakfast or have a party and have set out a bunch of things. So if you're in a share house and you do something in the kitchen, you've generated a lot of dirty dishes, everybody in your share house is going to hate you. So you have to make sure that you're tidying up after yourself and leaving the kitchen the way it was. Otherwise, there'll have to be some kind of house meeting and everyone will get together and have scornful looks at each other and complain about each other. More of an issue now that we're all stuck at home. I'm sure there's more share house kitchen friction going on, but that's something that everyone's just going to have to work out. Here's an example of a function prolog and epilog. A general example which you could expand to work with a function that you'd like to do. So we're going to assume in this function that we've got three parameters. One's in R0, one's in R1, and one's in R2. So the very first thing we do is we're going to put R0, R1, and R2 onto the stack. And then we're going to put LR onto the stack. So we're decreasing the stack pointer by 12 and then decreasing it by 4. Then in our body, we're going to do a bunch of stuff, leave the return value in R3, and start this process of actually getting out of our function. So the first thing we need to do is make sure our return value is in the right spot. So we're going to move R3 into R0. Then we're going to do our pushes in the opposite order to pop things back. We're going to pop out LR into our link register, but we're not actually going to pop out all of these parameters, because if we popped them into R0 to R2, we'd be writing over R0, which we were using for our return value. So all we're doing is just balancing out the initial push with the 12 bytes, the 12 memory addresses that we need to cover that R0, R1, R2 parameters. And then finally, we BXLR out of our function. Not too complicated, but keep an eye on it and make sure your pushes and pops balance out when you're writing a function. I think we're getting towards the end of the content for the day. Just let me check where we're at. Oh yeah, good. There's this idea with functions of each procedure in your program, each function having a frame in the stack. So a frame in the stack is going to contain all of this work that's going on, and it will contain multiple little places where you've stored all this data. You've stored your return address, you've stored your parameters, you've stored some local resources, you've some local variables and some saved resources. And this is how it might look. You've got your stack, and when you first start your program, you're going to start at the base of the stack. The first thing that's going to go there would be maybe some global variables. So your program starts, you have to save some important data, the location of your frequency if you're playing back a sound or something. And then you might run a function. So then we're going to do this function prologue, save our parameters, save our return address. Then we're going to do some work in our function, which might also use the stack, saved resources and local variables. So this function can be sort of represented as a list of little boxes of data in the stack. Oops. And then when we bx from our function, first of all, we kind of decrease or increment back the stack pointer back to here. And then we're going to pop that, and then we're going to increment back to here as well. So as we exit from a function, our stack pointer goes the other way, and we clean up our stack frame after ourselves. So here's a little example of 3 functions within each other, because this is when our stack frames are going to get a little bit more complicated and we have to be careful about what's going on. So the first function is going to push a parameter and then push the link register. Then it's going to run a middle function. The middle function is going to push a parameter, its parameter, and push the link register. And then we're going to run another function, and the inner function will do some other stuff. And then just BXLR back to here, which is going to clean up after itself, pop off those 2 values. And then BXLR, this one's going to clean up after itself, pop off those 2 values, and then BXLR. So now we can look at what this looks like in the diagram form. We've got a much more complicated diagram now. So we've started with our outer function. The first thing our outer function does is push its parameters, push its return address. It might do pushing some other resources if we had a more complicated function. And you can see that this one is where it pushes onto the stack the things that the function itself has to save, the callee saved resources. Then it's going to make some room for its local variables, as we were discussing before. And then in this point in the stack frame, our function knows that it's going to have to call another function in a minute. So it has to maybe push some caller saved resources. What would the caller saved resources be, right? It might be 0, 1, 2, 3. If we were expecting to use those later, we might have to push those into the stack so that they're going to be okay when our function returns. Then it calls BL on our middle function. The middle function does the same thing. Parameters, return address, saves its callee saved resources, R4 through R9, then does its work, local variables, and then the middle function wants to call another function, so it's got to save its caller saved resources, right? And then we got the inner function starting a stack frame. And the inner function is certainly going to save its parameters and return address and do some work, but it's not exactly going to, it's not going to have to call another function, so it doesn't have to do any more call or save resources, and it's not going to have to go any further in the stack. So this is why this is called a frame. Each one of these little parts of the stack each function is represented by a little bit of the stack, which has a similar structure. Each of these functions has a frame to give it some, where all of these things are located. Now what you might find is if you've got some stuff stored in your local variables, suppose in this middle function, and it wanted to refer to something in there, it might be a little bit difficult to refer to it. Maybe your inner function actually might want to refer to it. It's difficult to refer to that from the current stack pointer. So sometimes there's another pointer called the frame pointer, which would actually point to this very first address in each frame, FP. I don't think we have frame pointer on the Disco board. Or you can make your own, but there's no specific register dedicated to being a frame pointer. Adam says this is an agreed order upon for the stack frames. If it's in the AAPCS, then yes. Otherwise, you're allowed to generate your own. But as long as you're storing your data which you need for later, and you're storing your call save resources, then your frame is going to work. But if you don't take care of these details, then it's not. Someone else has asked a question, which I'm just trying to work out what it was. So R1, R2, just for random parameters. I think that in the previous example, I was using R1 and R2 either for the input parameters of a function, the arguments of the function, that is data going into the function. And then during the function, I would also use those low-valued registers just for doing general calculations. If you need to do a calculation that takes a couple of steps, you'll probably use R1, R0, R1, R2, R3 to save some numbers in between. Yeah, Adam, or to those asking about whether this is there's a canonical order for stack frames, I'm going to call this the COMP2300 canonical order. And we can have a look in the AAPCS later to see exactly how it's set out. So, as you might see, as we're going through our program, we haven't actually done any of our work yet. These are just all these functions getting themselves set up. So the SP, the stack pointer starts here. Whoops. The stack pointer is going to start here. And then as your program runs, it moves down a bit more, moves down a bit more. This function finishes, moves up there. Then another function gets called, moves down, moves up, moves up. So it's going to, as we say, zipper up and down. So moving up and down the stack, pointing to different locations as functions start up a frame, finish one off, and delete their data off the frame. So it's a moving target. It's always going different places as different functions are in control. So there's lots more to say about this. There's lots of things that you can put in your stack frame. I talked a little bit about the frame pointer. What you should probably know is that the ARM v7 procedure call standard uses registers a lot for the argument, the parameters of a function return values. There's other ISAs and calling conventions which would use the stack a lot more. And in fact, in the olden times, we had much simpler computers. There was a tendency to use the stack more because registers were precious. You didn't have many general purpose registers, and you wouldn't be able to do much calculation in the registers if you didn't use the stack. So another thing is that even though as we're doing this stuff in assembly, you think you know what a function looks like, if you're using a compiler to go from a high-level language like C or Java into assembly code, you're almost certainly not going to get code that you recognize. It won't be what you expect. the optimizing compilers have all kinds of tricks to optimize all your code away and make your computer run faster, which is great. But when we're being assembly programmers, we can't rely on it. I'll show you in week 6 some examples of how that works. The final one is that recursion is an interesting case, it's an interesting case to have to test yourself to use a stack correctly and pass data around. You've got a whole lab to work on recursion, but I think I might just have time to give you a little demo so we can give that a try. I should say finally that these are all just conventions. The disco board is not going to crash and tell you you haven't obeyed the convention, like if you do your instructions incorrectly. So it's your job as a programmer, in collaboration with every other kind of programmer, to obey these rules. And when you're programming in assembly, you're doing every job. You're directly controlling your computer. Yeah, so as an assembly programmer, you're being an operating system programmer, you're being a compiler programmer, you're just compiling things yourself. You're making your own libraries, you're making your own application, you're in complete control. So if you want to have another convention, that's up to you. Nothing's going to go wrong as long as you satisfy your own rules as far as they go. But I guess I should note that if you write as the answer to an exam question, well, it's this way because I've invented my own convention, I hope that you have a good justification for it, so to get away with that. We're going to go into question time, but I might also do a little demo in a minute. Why not? There's no one else to kind of come in here. We may as well give you guys a demo. I'm going to leave the chat on, and we'll see what people want to say. Any questions? No. I might save the recursion demo until another time. I've got something else I might show you though. Let's have a play with this decrementing and write back store command. So suppose I want to store a couple of values in the stack. So I might start off with stir. I'm going to put something in R0 first, mov. I'm going to store R0. And it's going to be in the stack pointer, -4, of course. And I'm going to make sure that I use my exclamation point in the right place after the brackets. So I put that in the first location in the stack. I'm going to put something else here. Maybe 9 SP -4. Oh, 2. That's not going to work, is it? Store 0. And I'm going to do something again. This is me putting a bunch of working data. So imagine if I'm in my function, I might be putting in some local variables before I do some work. 6. You can just use that same line. So this is a pretty simple little function. I just want to be storing, I just want to store a little bit of data onto the stack. But now if I might do some other work, right? Other work could go along with things. Not really too concerned about where all this data is. And then I might want to access maybe number 9. So then I'm actually not going to change my stack pointer because I just want to load this bit of data back. I already stored it. I just want to load it. So I'm going to load it from the stack. And the question is what my offset should be at this point. So you know that the stack is always pointing to the stack pointer is always pointing to the previously occupied location as long as I followed the rules, and I think I have. So the stack pointer ought to be pointing to this number 1 right here. Then if I added 4, I'd be getting number 6, and if I add 8, I'll get number 9. So I should be able to do offset addressing. I'm not doing write back now. No need for an exclamation mark. Let's get number 9 back in R0. So this gets me my local variable stored there, which happened to be 9. So let's see if this is going to work. I see a few questions popping up. I'll get to those in a minute. So first I load 7 into R0. Let's just have a look at the stack pointer. Oop, too far. Stack pointer is pointing at the top of the stack, 0x2001800. So now it's moved down a little bit. Put number 9 into R0. Stack pointer moves down a bit. Put number 6 in R0. Stack pointer moves down a bit. Put number 1 in R0. Stack pointer moves down a bit. So now we can see if I've done the right thing. Am I incrementing correctly in order to get back my number 9? You can see that I have. I've gone back. I didn't need to go back 0 if I just restored from SP. That would be this location. Restored from SP plus 4 is this one. SP plus 8 is this one. And if I'd gone SP plus 12, it would have been this one, number 7. This is full stack. Yeah, someone's just asked in the chat, isn't this full stack? It is full stack. That's how V7 works, and that's how I've set it up. I'm doing pre-offset in each of these ones. That means I'm using the exclamation mark. So this means that first define SP to be SP minus 4, then store R0 at SP, right? And because it's full stack, SP is always pointing to the last stored value. Same thing here. First SP minus 4, then store R0 at SP. Yeah? Yep, so do remember that someone's asked a great question, which is, why is there so much more memory to use in the stack than there is in registers? Well, remember that in our memory lecture, we talked about how expensive memory was. And we were discussing that the SRAM on your disco board is much cheaper than the register memory in your inside the CPU. So the memory that's absolutely closest to the working bits of the CPU, the arithmetic logic unit, the decoder, the loader, those are the registers. They're literally built into the CPU, and the arithmetic logic unit has its little wires directly stuck into those memory circuits. But those memory circuits actually take up a lot of space. I'll show you in another lecture a simulation of an older CPU, one of the first CPUs used in personal computers called the 6502. And when you look at the die of the 6502, most of it is the registers. And then there's a little bit of it for the ALU, because those registers were so expensive in terms of the number of transistors that are required to build the flip-flops and build out the registers. So you do tend to have small amounts of memory and registers, particularly in earlier machines. There were fewer registers because they were so expensive. Now, current machines have more registers, but also we've got much more data requirements. So you might have, on our disco boards, we've got 16 registers. On other architectures, we've got 32 registers. But even then, that's not that much data. So you might want to be wanting to use much more data. You have to store it in memory most of the time. You only have it in your registers for a moment, just as you're operating on it. Then you get rid of that out of the registers and go back to leaving it in memory. And that's as you're learning in the labs, that's this load, twiddle, store architecture, where you load something from memory, do something with it, then put it back really quickly. And that's what the kind of pattern we should be using for most of our programming. Someone's asked in the other chat, why did I put the 8 inside the brackets? Why did I put the 8 inside the brackets? So there was a reason for that, and I'm going to show you what happens. It'll still work. If I put the 8 outside the brackets, then I'm going to do a load into R0 what is stored in SP, and then I'm going to write back to SP plus 8. So this is basically doing a pop of 2 values back to this one and loading that one. It's incrementing after, post offset. So it'll still work, I think. Let's give it a go. Seven, storing something into the stack. 9, storing something into the stack. 6, storing into the stack. 1, storing into the stack. Okay, now I get to my post offset address, and you can see that when I do this, it's gonna load my number, but then it'll actually load this one, I think, and update. So it loaded number 1, which was stored at the top of the stack, and then it's popped off 2 values and moved SP back to here, which was not what I wanted. I wanted to load number 9, and I didn't want to change my stack pointer at all. I just wanted to access something I'd previously changed. So I guess when we were talking about a stack before with the plate analogy, I guess you can't pop off plates until you're working from the top, but you can also sort of look in the stack and see what you've got there. So there's potential to be kind of getting in the stack without changing SP, which is what I wanted to do. This one is correct. This one is not correct. It's going to do post offset. This will do post offset. So loading 1 into R0. And then moving SP 8. Yeah. Oliver says, well, maybe if cost size wasn't an issue, would a disco board run faster if you replace the stack addresses with registers? Absolutely it would, because whenever you load, that takes an extra cycle to get the data from memory into the register, and then you can do the operation you want. But I think that you would end up with it's not possible probably to have a CPU with sufficient registers, right? Your CPU would have to be wired directly into all of your memory, and you wouldn't be able to like fit into one instruction enough bits to like store the address of all those memory locations. So at the moment, our instructions only have to deal with a maximum of 16 different register locations, except for the loading and storing instructions, which can look at the whole address space. So if you wanted your regular instructions to be able to look directly into memory, first of all, there'd have to be physically little wires all between your ALU and all of these different bits of memory, which is impractical. There's physical reasons why that wouldn't work. And secondly, your instructions would be super long because you'd be storing memory addresses like directly in them, and that would actually make them slower, right? So it would cause your disco board to be slower. I guess if the question is, if we didn't have to worry about things being practical, would an impractical situation be good? Then yes, it would be impractical. But if we're not worrying about practicality, we don't have to worry about that. Yeah, someone mentions in Twitch chat, you would need a register to hold a register's location, which would not be very useful. Any other questions? I don't want to let our lecture times go on too long, so I'll close it down in a minute. I just check my stats, the most important thing, knowing how many people are watching. Oh, there's not only a few watching now, so maybe people have gotten tired of me. Check out my analytics. Yeah, definitely a few people watching. Okay. Thank you so much, everybody, for watching and coming up with great questions. It was particularly nice to see questions from a few new faces, including from one little extra question from Mitch I might answer in a minute. I know there are some people in the chat who are regular attendees in lectures. They're the ones who are sort of in the front row of the lecture. They're also in the front row of the streams. But if you're here watching, know that I really want to hear from you, and it's wonderful if you do think of something to ask. Then it certainly helps everyone. I'm gonna go to try one more thing, which is Mitch's idea is, can we look at the stack in the memory view? We can, right? But it's a little bit annoying to try to find the right value. Because it's backwards, we have to start at the bottom. So what is the stack's address right now, the lowest address? 0x2001 7ff8, 32 bits. So this is some bits of my stack right now. Yeah, cool. Well, I might go to the ending theme for a little bit and catch you guys later. Thanks, friends. Really great to chat with you all and have this stream again. Turn my mic off. I'll catch you all after the mid-semester break. So we're going to have 2 weeks of basically break. You've got some time to work on your assignment for another week, and then I'll be back with a lecture in new week 6. It seems like such a long time. We never quite get into a good rhythm in this course with crazy stuff happening this year. But it will be good to see you all when we're back. I might be able to record some extra stuff over the holidays if there's some questions.